Hello, my name is Jiajia Li. I come from Computational Science and Engineering, Georgia Institute of Technology. My project is about an input adaptive and in-place approach to dense tensor times matrix multiply. This is a joint work between two research groups, HPC Garage and InTensLi. HPC Garage is led by my advisor, Professor Richard Wooduk. His research focuses on high-performance computing. InTensLi is led by Professor Jimeng Sang. His research focuses on data mining and machine learning for health applications. Let's see what is tensor and tensor applications first. Tensor can be interpreted as a multidimensional array. We draw a three-dimensional tensor here. Vectors and matrices are special cases for tensors. Tensor dimensions, also called tensor mode or order. In this presentation, I'll call tensor mode. We focus on dense tensors in this work. TTM is a basic tensor operations, which is short for tensor times matrix multiplication. Tensor applications include quantum chemistry, quantum physics, signal and image processing, neuroscience, and data analysis. Now let's focus our TTM algorithm. This operation is to given an input tensor x and to multiply a matrix U to get an output tensor Y. The operation is based on the mode N. So the traditional TTM algorithm is to transform the tensor X to the matrix Xn and then do the matrix multiplication to generate another matrix Yn. Then Yn is transformed back to a tensor Y. In this process, according to our experiments, the two transform stages consumed about 70% of the total running time of TTM operation and 50% of the total space. So that's because the transformation needs physical reorganization of the tensor. So in our work, we proposed an in-place tensor times matrix multiply in TTM algorithm by avoiding physical reorganization of tensors. And I also built an input adaptive framework in InTensLi to automatically adapt parameters and to generate the in-TTM code. From here, we achieved 4 times and 13 times speedups compared to the state-of-art Tensor Toolbox and Cyclops TensorNet framework tools. Let's first see our InTTM algorithm. The input is a dense tensor, a dense matrix, and the integer A, which present the mode N to do the tensor times the matrix. The output is another dense tensor Y. As we say, our InTTM algorithm also based on matrix multiplication, but we don't need to physically convert the tensor to a matrix. Instead, we combine contiguous tensor modes and do in-place tensor computation here. So this if and else are two situations for different strategies. And in the same time, we need a bunch of loops outside the matrix multiplication kernel. So our InTTM algorithm eliminates the arithmetic intensity of the original TTM algorithm. And also we say there are 4 parameters which are used in our auto-tuning frameworks. M1 and MC are mode sets for loops and innermost matrix multiplication, and PL and PC are the number of threads allocated to loops and matrix multiplication. Our InTensLi framework takes the input parameters such as data layout, tensor dimension, tensor size, and the mode N to do the TTM operation, and also consider the hardware parameters such as the maximum number of threads. We also build the matrix benchmark to test some thresholds to help to decide the 4 parameters here. In the next step, we use parameter estimator. One part is mode partitioning, and the other is thread allocation to separately decide ML and MC, and then PL and PC. And then we use code generator part to generate our InTTM code. Our InTTM algorithm can directly call any matrix multiplication libraries such as Intel, MKL, and Bliss. Now let's see our experimental results. We do our test on two Intel platforms. One is Core i7 and one is Xeon E7. We employ 8 and 32 threads respectively on the two platforms. And the performance, the leftmost bar is our InTTM performance, and then the Tensor Toolbox, then CTF. And this bar is we use baseline TTM algorithm, but without counting the transformation time. That means this is the highest possible performance we can get for TTM operation. So from here we can see we obtained 4 times and 13 times speedups compared to Tensor Toolbox and CTF, and we also get very close to game-only performance. That means we get the highest possible performance. Sometimes we can achieve higher performance than it. That's because we used our InTensLi auto-tuning method. So, we can choose the optimal parameters for our InTTM algorithm, which will benefit the performance. Now that's all for our project. Thank you for your attention.